Good morning, everyone. Today we shall discuss about one more algorithm called as Bellman Ford algorithm. This algorithm is used to find out all pair shortest single source shortest path. Single source shortest path means you have to find out the shortest path to all the vertices from one source. You may select whichever source you want. From that particular vertex to all other vertices, what is the shortest distance you need to find out. For that, you can make use of Bellman Ford algorithm. Uh, Already, we have solved single source shortest problem using Dijkstra's algorithm. Uh, but in Dijkstra algorithm, if there is a cycle, it is not like always you not get the correct output. So, which is solved in the case of Bellman Ford algorithm. Algorithm is as follows. First, you will be initializing the distance of all the vertices to infinite. Okay. If there are 8 vertices, you will assign infinite value to all the vertices, and then distance of source is equal to 0. First, source to source will initialize that distance to 0. Next is there is a for loop here for for loop 1 to set of vertices minus 1, number of vertices minus 1. So this for loop will be executed. If there are 4 vertices, it will be executed 3 times. Number of vertices minus 1. For loop will be executed n minus 1 times. Inside the for loop, what you must do is in each iteration, you should check the distance of all the edges. Okay. If there are 4 edges, it will take 3 iterations. All 3 iterations, what you must do is you have to check the distance of weights of all the edges. How we are going to check? We will check the weight of all the edges and update the distance of that particular vertex. Okay, UV, consider edge UV. Check the distance of V, whether if it is greater than distance of U plus weight of UV. If it is greater, then distance of V is equal to update it. Okay, if it is less, don't do anything. Okay, this you'll understand with the example when I very simple algorithm. Okay, we'll consider one vertex at the time, and we'll update the distance of each vertices. And next part, one more for loop is there. This for loop I will explain in the end. Okay, so this is Bellman Ford algorithm. We shall see this algorithm with respect to an example itself. Okay, first iteration, we have not started the first iteration. Before that, see this infinite, above each vertex, we have written infinite. This is nothing but distance. Okay, distance of each vertex, we have initialized it to infinite, and distance of source is 0. Distance of each vertex, we have assigned the value infinite. Okay, that was the first step. Before we start the iteration, we have to initialize all the vertices to distance of all the vertices to infinite. So we have done that. Next, we will start the iteration. So here 8 vertices are there. So it will undergo 7 iterations. In each iteration, it will try to update the distance of each and every vertices. So 7 iterations it will undergo. We are in the first iteration. And what it must do is has to consider all the edges in the graph. And it is a directed graph. Be careful, it's a directed graph. S to A to B is not there. A to B edge is not there. It is B to A. So list down all the edges that are present in the graph. Okay, first thing you have to do is list down all the edges that are present in the graph. And in each iteration, you have to check all the edges and update the distance of each and every vertices. Okay, check all the edges and update the distance of each and every vertices. Okay, distance of UV. distance, this is edge UV. If you say take it as edge UV, distance of A is equal to 0 plus 10, weight of this edge. Okay, first we shall consider SCA, that is edge SCA. So distance of A is now infinite. Okay, distance of A is infinite. You can update it with 0 plus 10. If 0 plus 10 is less than infinite, then distance of A will be updated with the value 10. Is it clear? Distance of 8, right now it is infinite, but we have an edge from S. Okay, distance of S is 0. So 0 plus 10, it is less than infinite. So update the weight of A to infinite, 10. Okay, weight of A is updated to 10. Next, consider edge SG. Distance of G is 10, infinite. Now 0 plus 8, it is less than infinite. So update the distance of G is equal to 8. Okay, update G weight I have updated, A weight I have updated. Next edge is G to F. Edge G to F. So distance of F is infinite. Distance of G, 8 plus weight of this edge 1. 8 plus 1, 9 is less than infinite. So update the distance of F to 9. Okay. Next edge is F to A. Okay. Next edge is F to A. Already distance of A 10 is there. Now we got a new edge to A. Its distance of F plus weight. Okay. 9 minus 4 is 5. 5 is less than 10. Okay, 5 is less than 10. So update the weight of A. It will become 5. Here also you have to update it. Its weight will become 5. Next edge, FE. Okay, FE. See, earlier distance of A was 10 when we had only S to A edge. Now F to A edge, when we discovered, its weight will change to 5. Next, consider the edge F to E. Okay, its distance is infinite. We can calculate the new distance. 9 minus 1, 8. F to E is 8. Okay, distance of E is 8. Next, one more edge is there, A to E. Okay, so its distance will be 5 plus 2 is 7, which is less than 8. So change that to 7. Okay, next E to B, edge E to B. Distance of B is infinite. So calculate distance of 7 minus 2 is 5. So distance of B will be 5. Next, B to A. It's B to A. B to A. Already distance of A is 5. So 5 plus 1, 6. 6 is greater than 5. So don't change the distance of A. Here change will not happen. Next, consider B to C. B to C. Distance of C is infinite. 5 plus 1 is 6. 6 minus 6 is less than infinite. So update the distance of 6 to C to 6. Next, C to D. Distance of D is infinite. 6 plus 3, 9 is less than infinite. So update the weight of D to 9. Next, D to E. One more edge is there, D to E. Okay, distance of E is 7. Check the new distance. 9 minus 1 is 8, which is greater than 7. So no need to update the weight of this E. Distance of E is not updated. It will be 7 itself. So this is the end of first iteration. Okay, this is the end of first iteration and we got the distances as follows. Next, again, in the second iteration, we have to consider all the edges and check whether distances can be updated in the second iteration. S to A. Okay, distance again. You have to consider one by one all the edges and check whether distances will vary or not. S to A. Distance of A is now 5. Consider edge S to A. 0 plus 10 greater than 5. No need to update. S to G. Already 8 is there. 0 plus 8 is 8. So it will remain 8. G to F. G to F. 9 is there. 8 plus 1, 9. So no need to change this distance. F to A. F to A, 9 minus 4 is already 5. So no need to update. F to E. F to E. 9 minus 1 is 8. But here distance is 7. So no need to update. 7 is less than 8. Next, A to E. A to E. 7 plus A to E. 5 plus 2 is 7. Already 7 is there. No need to update. Next, E to B. 7 minus 2 is 5. Already 5 is there. No need to update. B to A. 5 plus 1 is 6. But here less than 5 is less than 6. No need to update. B to C. 5 plus 1 is 6. Already 6 is there. C to D. 6 plus 3 is 9. Already 9 is there. No need to update. D to E. 9 minus 1 is 8. But here 7 is there, which is less than 8. So no need to update. See, in the first iteration itself, almost we have got the minimal distance between source to all the vertices. So in the second iteration, there was no changes. Similarly, in third iteration, fourth iteration, graph will not change, distances will also not change. But according to algorithm, it will undergo all 7 iterations. In this particular example, distances are not changing. In some examples, we need all the n-1 iterations so that finally, from the source vertex to all the vertices, you will get the shortest distance. And here you can observe there is a cycle here, E to B to C to D and to E, again cycle. Okay, so in Bellman Ford algorithm, if there is a cycle, it will not create any problem. You can easily find out the solution. Here also cycle is there, F to A to E. Okay, cycle is there. So if there is a cycle also, it will not, no, this is not a cycle. Okay, here cycle, no other cycles are there. Okay, here is there, A to E, E to B and B to A. Here also cycle is there, but if cycle is present in the graph, it will not create any problem in case of Bellman Ford algorithm. And again, we can also consider negative weights. In Dijkstra algorithm, if you take negative weights, always you will not get the proper output. For that reason, Dijkstra algorithm, that is the drawback of Dijkstra algorithm. Negative weights, it will give the output, but always it will not be the correct output. Whenever we take negative weights for Dijkstra algorithm, so all those drawbacks are handled in the case of Bellman Ford algorithm. Cycles can be present, also negative weights can be present on the edges. So this is Bellman Ford algorithm. Quickly, we shall see one more example. So this is the given graph. 5 vertices are there. So it has to undergo 4 iterations. Before that, you initialize distance of all the vertices to infinite. Okay, distance of t, distance of x, distance of y, and distance of z. Okay, all these vertices distances, initialize it to infinite, and source is s. So distance of source is equal to 0. From s, we are going to start, and I have listed down all the edges that are present in the graph. And assigned it's, see, edge t to x means it's nothing but it will give us the distance of x. Okay, it should be x, not t. Okay, it's x. Edge t to x means it will update the distance of x. Okay, t to x means it will update the distance of x. So I have listed down all the edges that are present in the graph. So it will undergo 4 iterations. We shall see in each iteration how things will change. Okay, first iteration. As I said, it should be, it is not t, it is x. Okay, distance of x edge. I am considering we are starting with the edge t to x. Okay, t to x. And distance of x will be updated. You can see here, distance of t is infinite. Infinite plus 5 will also be infinite. So it will not change. Distance of y. Distance of y, t to y, edge, t to y we are considering. Infinite plus 8 is equal to infinite. Distance of z, edge we are considering t to z. Okay, t to z. Infinite minus 4 will also be equal to infinite. So we are none of the distances are getting updated. X to t. Okay, x to t. Distance of t is trying to update it. Infinite minus 2, it is also infinite. Distance y to x, y to x. Okay, infinite minus 3, again it will remain infinite itself. Y to z, y to z, infinite plus 9 is also infinite. Next z to x, okay, z to x, infinite plus 7, again it will lead to infinite. Next s to t, edge s to t. Okay, edge s to t, it will update the weight of d to t, distance of t. It will update the distance of t. 0 plus 6, distance, the source value is 0, distance. 0 plus 6 is less than infinite. So distance of t is updated to 6. Next, s to y, edge s to y. Okay, 0 plus 1, 0 plus 7 is less than infinite. So distance of y is updated to 7. In the first iteration, only we got the distance of t and distance of y. So which will be updated. Distance of t is equal to 6, distance of y is equal to 7. Is it clear? In the first iteration, only distance of two vertices got updated. Okay, all other edges are, see, there is no order for edges. Okay, these two edges itself, I should, if I have taken in the beginning, all other vertices distance will be updated, but I have taken it in the last. Okay, edges you can take in any order, but within 3 iteration, anyhow, distance of all the vertices will be updated. In the first iteration, in this case, only distance of t is updated and distance of y is updated. So we shall see the second iteration. In the second iteration, okay, in the first iteration, we have updated distance of t and distance of y. So in the second iteration, we shall see edge t to x I will take. Consider edge t to x, t to x. Now we got the distance of t. So 6 plus 5 is less than infinite. So update the distance of x to, this is distance of x. So update the distance of x to 11. Okay. Next, consider edge t to y. T to y, 6 plus 8, 14. But it is greater than 7. No need to update this distance. So distance of y, we will keep it as 7 itself because 14 is greater than 7. Next, t to z, 6 minus 4, 2. So distance of z is equal to 2. Okay, t to z, distance of 6 minus 4 will be equal to 2. So distance of z will be 2. Next, y to x, 7 minus 3, it will be equal to 4. So distance of x is equal to 4. X to t, okay, in the order x to t, x value is, we have updated the x value. Okay, x value was 11. 11 minus 2, 9. Okay, x value was 11 here. We have updated it. Distance of x, 11 minus 2 is 9, but 9 is less than 6, so we will keep it as 6, previous distance itself. Next, y to x, 7 minus 3. Okay, y to x, 7 minus 3 is 4. Here infinite 11 was there, distance of x. So 4 is less than 11. Update the distance of x to 4. Distance of x will be equal to 4. Next, y to z. 7 plus 9, 15. Okay, distance of z, will it be 15? You can see here, distance of z already we got 2. So 15 is greater than 2. We will keep 2 itself. Next, distance of x. Distance of x, previously it was 11. And then distance of x was updated to 4. Okay, earlier it was 11. Now it was updated in between to 4. Now we shall see z to x. Z to x, what is distance of z? 2. 2 plus 7, 9, but 4 is less than 9. We will keep it as 4 itself. Next, s to t. S to t, 0 plus 6, it's 6 itself, no update here. Next, s to y, 0 plus 7, it's 7 itself, no updates here. So in the table, you just see distance of x, 3 times we have calculated, but this is the least distance, so we'll write this in the table. Okay, 4. Next, distance of z is 2, so that will update in the table. Okay, so distance of x is 4, distance of z is 2. This is after iteration 2. Next, we shall go one more iteration, third iteration. Distance of x. Okay, no update here. Distance of x already small value is there. It's not 11, it should be 4. Okay, distance of x is 4. 6 plus 5 is 11, which is less than 4. So keep it as 4 itself. Next, t to y. Distance is 7. 6 plus 14. 6 plus 8, 14. Less than, greater than 7. So keep it as 7 itself. Next, t to z. Okay, t to z. 6 minus 4. 2 is there. So 2. Next, x to t. Okay, x to t. Earlier distance was 6. Now x to t means 4 minus 2 is less than 6. So x to t, distance of t will be updated to 2, which is, okay, it should be 2, which is less than 6. So instead of 6, we will write 2. Next, y to x. Y to x. 7 minus 3, already 4 is there, no update. Y to z. Y to z, 7 plus 9, 16. No need to update, it's already small distance. Next, z to x. Z to x. 2 plus 7, 9, which is greater than 4. No need to update. S to t, 0 plus 6. Okay, 0 plus 6, it is greater than 2. No need to update. Next, s to y. S to y, no need to update here also. Only thing we have update is distance of t. Okay, which was updated to 2. And we shall see one more iteration. T to x. T to x. Again, it should be 4, not 11. Okay. T to x, distance is 4. No need to update. T to y. T to y. 2 plus 8, 10. Already 7 is less than 10. No need to update. T to z. Okay, t to z, distance is 2. Z distance is 2. But new distance is 2 minus 4 is minus 2. So this distance will be updated to -2. Okay, this is updated to -2. X to t, known change. Y to x, distance of x. Y to x, again no changes. Y to z, 7 plus 9 is less than 2, no changes. Z to x, again no changes. S to t, S to t, okay, 2 is less than 6, no changes. S to y also no changes. So this is the new distance, and this will be the final graph after iteration 4. Okay, in this graph you can see 5 vertices are there. We took 4 iteration. So in each iteration there was some changes that was happening. So this is the shortest distance from S to all other vertices in the graph. Finally, at the end of 4th iteration, we got the shortest distance from source vertex. Okay, this was the source vertex. From source vertex to all the vertices. From S to T was 2, S to X was 4, S to Y was 7, S to Z is -2. So we'll get the distance array, which will give us the distance from source vertex to all the vertices, shortest distance from source to all the vertices. Okay, so this is Bellman Ford algorithm. I will consider the graph. It will undergo certain iterations. In each iteration, it will update the distance of the particular vertices. Okay, and there was last part of the program which algorithm, and this part will check whether there are negative cycles in the graph. If there are negative cycles, then Bellman Ford algorithm will not work. See, cycle is allowed. Okay, there is a cycle here. Cycles are allowed, but it should not be a negative cycle. What is negative cycle? You can see if you add up these things, 5 plus 3 is 8. 8 minus 10 is -2. So negative cycles, if there are negative cycles in the graph, then Bellman Ford algorithm will not work. To detect that negative cycle, this last part of the program is used. We'll sum up and we'll check whether there is negative cycle or not. If there is a negative cycle, then Bellman Ford algorithm will not work. Cycles are allowed, but negative cycles, for negative cycles, this algorithm will not work. Is it clear? So this is Bellman Ford algorithm to find out single source shortest path. That is the path from one vertex to all the vertices. Okay, all of you mark the attendance, and we shall see the next topic in the next class. Thank you.